session will be recorded and uploaded to the CDSE Days website in about a week or so that anything that Andrew and Sarah present today, you'll be able to go back and see in more detail. So our workshop presenters today, Sara Metcalf is an associate professor in UB's Department of Geography. Sara earned her PhD in 2007 from University of Illinois before joining UB. She works in the area of dynamic modeling, system sciences. Joining her is Andrew Crooks, who joined UB just this past fall, 2020, as a professor in geography after coming to UB after spending several years at George Mason University. Andrew earned his PhD from University College London and is an expert in geographic information science. So today, Sara and Andrew will introduce us to a computational tool called agent-based models, which simulate the dynamics and interactions of decision-making entities. ABMs have been used in applications from epidemiology to macroeconomics and lots of things in between. If audience members have questions, we ask you to put them in the chat. We'll have several folks monitoring the chat and raise questions then to Andrew and Sara and bring your questions to their attention. So without further ado, you want to take it away, Andrew and Sara. Thank you.
Thank you.
Thank you, Bruce. Okay. Oops. Okay. So what we're going to do in the next 2 hours is to walk you guys through what is agent-based modeling. And then that's a very brief introduction, by the way. Sara and I both offer variations of courses on this, which take a whole semester. So we're trying to distill semesters or years worth of work into a 2-hour tutorial here. And then we want to go into how to build a model and considerations for building models, but actually walk you through, so you guys as the audience will go through and actually build a model with us in a agent-based modeling toolkit called NetLogo. After the tutorial, we'll go into various applications that Sara and I have been exploring over the last while, and also dig into some of the thorny issues where Sara is sort of leading expert in this area with respect to model analysis and calibrating models. And then we'll wrap up with a discussion. Anything you want to say, Sara? Or?
Yeah, well, no need to say, but I will just say, yeah, we're front loading the tutorial. It shouldn't take more than an hour to go through, and we're gonna try to do that in the first part of this so that we can be a little bit flexible with time. So we do encourage questions as Bruce said, and so please feel free to type stuff in chat or use the raise hand signal as needed. We can go ahead.
Okay, so I don't know how many people see, well, Sara and I actually don't know how many people have actually ever experienced agent-based modeling before. So the general question we have is, have you ever seen an agent-based model before outside of UB? And, most people will be surprised to realize that agent-based models are used a lot in the movie industry. My favorite is Doctor Who and the Daleks in Doctor Who. Often these are little computer programs doing things like trying to attack the Doctor, right? Or if you've seen like the big fight scenes in Planet of the Apes or Lord of the Rings, these entities are not people; they are agents, entities being programmed to do specific things, and through those interactions, we get something emerging. So fight scenes or swarming over walls. If you watch World War Z, and there's sort of zombies going over the walls in Israel. But lots of movies are utilizing agent-based modeling to basically save money. And and also it's quite interesting, massive, when they first started creating agent-based models and doing the rendering and the fight scenes and things like that, they needed supercomputers to do this, because the processing and rendering of these things is super computationally intensive. But normally my parents always ask me, what is agent-based modeling? And I try to explain that through things like this. But from an academic point of view, really what is an agent-based model is a simulation. We create an artificial world. We are sort of the gods of our creations in this sense. Within these artificial worlds, we populate it with people or agents. It doesn't have to be people per se. If you're in ecology, they could be like deer or fish. Individual-based modeling is what it's going to be called, or they can be households or they have to be some type of entity. These entities are given rules. So basically, if-else statements, if you're familiar with programming, and if a certain condition is met, you do something. Else, you don't do something. So, for example, if a fire alarm goes off, I then get up and leave the building. Else, I stay here for another 2 hours, or something along those lines. Within agent-based models, we also have agents interacting with each other, and this is key, because what we do is think about disease spread. COVID is a classic example of that now, right? You get COVID by interacting with other people, right? And we want to capture those interactions in simulation, but capture those interactions at the individual level, represent the individuals in these models. And
can I just add? Oh, go ahead, and then I want to add something, Andrew.
No, please. I'd finished actually.
Okay. I wanted to add one of my favorite definitions of an agent is a thing that does things to things. And so it fits very well with the object-oriented world of programming, and the rise of agent-based modeling has been facilitated by that facility, and also, of course, the sheer computational capacity that's now available for simulation modeling. But we can think of, or another of my favorite ways to think about agent-based models are to think of the universe as a hierarchy of decision rules, and you have the privilege of being able to access that knowledge from within the agents, and then all the limitations of those agents' knowledge, and then also still aggregate up to whichever scales are appropriate. And Andrew, we didn't specifically discuss this, but I wondered if you have any comments on the distinction between agent-based versus individual-based, if that's anything that you would have a comment on.
So in the old days, individual-based models used to come from ecology, and they were very stylized on empirical data and things that people had collected, say, look like movement patterns of sparrows or whatnot. But over time, I think as individual-based models have added more behavior rules to them, and agent-based models have added more sort of empirical grounding and things like that. They're very similar concepts now. But the individual-based models for me came from ecology rather than the social sciences, while ABM sort of evolved from.
You hear the term also in epidemiology, and I guess what I tend to think the distinction is, but you can correct me if you think differently, is that is about the decision-making aspect of the entity. So in a purely epidemiological model, we're not necessarily representing the full cognitive response. But once we think of agents, we're actually thinking of agency, and that reflects this human decision-making capacity, whether or not you're thinking of individual people or households or organizations or whatever. There's some element of that.
Yeah, no, that's very true, actually. And, I guess the contrast is also, compared to all the other modeling styles, this style of modeling really is on agency and individual agency as well, which I think it makes it unique, but also one of the biggest challenges, because human behavior is really hard to understand, and what drives one person doesn't necessarily drive another person in these types of models.
Okay, well, thanks for addressing that. You can feel free to proceed to the next slide as needed, because this wasn't
Okay,
unique to this slide discussion. Thanks.
no worries. So types of problems agent-based models. So this is types of problems agent-based models can explore. They can explore a whole range of things, really, from the micro movement of, say, basketball playing, and exploring the notion of the hot hand effect. Is that guy on a streak or not? So sports analytics, I know that's CDSE was talking, Bruce, you talked about, I know Bruce talked about sports analytics the other day. How can we use models to explore those sports analytics to the micro movement of pedestrians over, these are short-term models over seconds, minutes types of things. And we can use models to also explore things much over longer time frames as well, such as migration over, economic migration over years or decades, and nearly anything in between. I mean, agent-based models have been applied to a whole range of different types of phenomena. This at various spatial and temporal scales. And this is slightly, this is very much a geography sort of slide, but as Bruce mentioned in his introduction to us, agent-based models are often being used extensively in economics. The people who used agent-based models to understand the decimalization of the NASDAQ. Southwest Airlines have used agent-based models to look at how they handle cargo, and also behavioral routing, behavioral seat assignment. How do people choose what seats they live in or want to sit in? Well, one does live in an airplane, I guess, while it's in. When you go to Disneyland, when you can, or Disney World, you can buy that ticket to jump the queue to get preferential treatment. That rationale came from an agent-based model. Agent-based models are being widely used in disaster management, especially wildfire scenarios. There's a company out of Santa Fe, New Mexico, called SimTable that specializes in using agent-based models to help track and plan and track fires, and also try to mitigate against wildfires inside of this. Epidemiology, especially with COVID, ABMs have been widely used, and same with pedestrian models and traffic simulations. Some of the really wide areas of applications, I think, when it comes to this, and also mainstream. There's commercial companies. Sara uses a toolkit called AnyLogic, and I think you said AnyLogic is the first agent-based modeling toolkit.
They say, I said they say that they are the first commercial agent-based modeling platform. So I believe, I mean, they said that. I think it's still true. I guess if they're the first, it should still be true, regardless.
Yeah. So agent-based modeling sort of evolved in the 1990s, or became dominant, and then by 2000s there was an uptake of it. But it's not just academic research, is what I'm trying to say here. It is being used outside of academia for planning. The Hajj the Hajj in Saudi Arabia used agent-based modeling to redesign parts of the routes that they have there. Agent-based modeling has therefore become sort of more mainstream over time, is sort of what I'm trying to say there.
So this was, do you want me to comment on this, or do you want to say something first, Andrew?
No, please go.
Okay. So this was a slide that I had, I've used quite a bit in terms of framing the modeling process. I come at this from a broader systems perspective, and in particular the tradition of system dynamics, but the simulation modeling enterprise. And this, we found, Andrew and I, that we sort of agreed upon this, and we'll see more of that in the next slide. And coming at this also as geographers, we recognize, that models are, maps are a kind of model too. And when we do, models and data structures in GIS, these are a form of models. So when I speak of simulation models, I'm referring to dynamic ones. And in the system dynamics tradition, we're thinking of how does structure of the model create the behavior? That's the common theme in the system dynamics tradition. And this applies regardless of whether you're implementing it using ordinary differential equations or agents that are networked together. But what sort of feedback mechanisms are there? What sort of delays in it? Those structures create the behavior of the system over time and space. And what we're interested in, this is a normative imperative to actually try to do something better about the system, to change the structure in, maybe making or breaking feedback mechanisms to, or adjusting the incentives for a certain kind of behavior to improve the behavior, to address a problem. It's taken as a given that we want to address a problem. Now, why is it an art as well? And this is where I think the analog to mapping is useful. There is some discretion in what's going to be included or excluded. And so that's always going to be there. And yet as the second bullet notes, a useful computer model, whatever type is implemented, we can think of as also, in addition to its function, as a simulation or prediction, is creating a form of knowledge repository. This can be useful for collaboration, and it sets up a laboratory by which you create experiments. So as we're considering this in the context of the data science, we'll come back to this at the end, is thinking about the data that you generate from the simulations is worthy of analysis in its own right. And we want to think of how to design artificial experiments that are informative in the real world, given that we always are going to have a simplification of the model. The model is inherently a simplification of reality, but that by making it computational, we can make sure that our assumptions are at least internally consistent, and then use them to help mediate dialogue with different stakeholders with different viewpoints, perhaps, or controversial differences of assumptions. So in addition to using models to predict, we want to use models to explore counterfactuals and alternatives and be able to envision different kinds of worlds. And then back to you, Andrew. Thanks.
Oh, that was great. That was very good. Very good. So when we build models, building on, I guess, Sarah's thing about idea, is that we're trying to build models of a certain problem domain. And, there's lots of questions that talk about what informs the agent's thinking here. As Sara mentioned earlier, here we are really thinking about agents and the cognition of agents and what drives their behaviors, and how can within inside of this. And a lot of the time we can use model to help, or we can build these decision rules based on existing theories out there. So maybe the theory of planned behavior, or Maslow's hierarchy of needs, which, meet your basic needs first before you can do self-esteem, making friendships, and so forth. But we can also use models to build theory as well, and also to test ideas and things like that we can't do in reality. Sometimes also when we building these models, what data we need to consider, what type of data do we need? Do we need data? That's the other question. The tutorial that we're going to run through in a little bit has no data in it. It's purely a thought experiment. That's fine, because the purpose of this model is more of a thought experiment rather than a model for prediction per se. But models are not always used for prediction purposes. I think this is something that many people forget.
Andrew, yeah. I'd like to add one to that, in addition to, so there are many different reasons you might build a model, as noted. And one, it might simply be to provide a counteracting sort of antidote to the feeling of helplessness about not being able to control the system. So by creating some sort of model to understand some aspect of that, gives you a means to at least get at the general patterns and trends. So we'll return to thinking about the patterns that can inform models and also patterns that come out of them. And what does that tell us about what can we learn about the real world from that? Anyway, back to you.
And going back to the pattern analogy, it's agent-based modeling is wonderful because often we can observe patterns around us. We can observe number of people infected, right? That's a pattern. We can observe urban growth and the extent of urban growth. and what I think is particularly interesting about agent-based modeling is that we can explore the various processes that lead to these patterns emerging. And I think that's something that is also very interesting to explore.
I just want to add, Andrew, that and so we may want to model things that we don't have observations for, and that's right and good. Like that's one of the good reasons to use models is for situations where you don't have directly observed data, or it might be unethical to obtain such data. But by you can make use of the simulated data then to inform these sorts of analyses. Okay.
Yeah. So once we've decided what type of model we want and the purpose of the model that we're trying to do, is it for sort of theoretical purposes or for prediction or anything in between, and there's umpteen reasons why one might want a model. We then have to create the model. Nearly all agent-based models now, the architecture is some type of object-oriented programming analogy, and you can roll your own program. You can roll your own ABM. Agent-based model. We can, if you want to just do it in Java, fine. If you want to do it in Python, MATLAB, you can do it in Excel if you really want to. But there's also a whole host of toolkits out there that allow that have been developed over years by academics, professionals, I guess, that we can use. Why might you want to use a toolkit? I like to use toolkits because I can focus on the modeling itself, not things that are not relevant to the model. So I don't really care about graphical user interfaces. I don't really care about synchronization and other things that you'll see in NetLogo. NetLogo takes care of that for us. Toolkits allow for sort of more ease to develop models over time, and there are lots of really good toolkits out there now for people who are competent and comfortable for Java. There's the agent-based modeling toolkit called Mason, which stands for multi-agent systems of neighborhoods or networks, or something that makes the end, so they can link back to Mason, which was developed from the George Mason University. Repast has been available since the early 2000s, developed by Argonne National Lab. It was very powerful. Both Repast and Mason allow for high performance links to parallelization. So Repast has a HPC, high performance computing plugin that one can use. We have commercial products you can get educational licenses for, like AnyLogic. There's some new Python toolkits emerging, and one thing I quite like about the Python toolkits is that you can use Jupyter notebooks, so everything is in one document. So which is not necessarily so all the way from maybe if you're collecting data, analyzing the data, to the model, to the outputs, all can be in one Jupyter notebook, therefore it allows for reproducibility. Mesa is one example of that by Jackie Kazel and David Mesado, the lead developers on that. And then sort of I'd say the most widely used, at least in an academic setting, especially for teaching purposes, is NetLogo. Or you can just create these models from scratch. And I don't think, yeah. Okay, so just to give you a sense, this is a simple NetLogo model, but it's here for two purposes. One, to show sort of the graphical user interface of the model, not the code, but just the graphical user interface, but also to sort of try to cement to you guys listening what is an agent-based model. So in this simulation, we have individual cars. These are our agents. These individual cars have been given very simple rules. Remember, we said we create this artificial world. This artificial world is a road here. Our agents are cars. We give them very simple rules. If there is a car in front of you, you slow down, which makes sense because you don't want to crash the car, right? And if there's no car ahead of you, you speed up, which is roughly how most people drive. If there's no car ahead of you, you guys probably go a lot faster than when there is cars in front of you. These simple rules apply to many entities or agents, cars in this example, lead to more emergent things happening, such as traffic jams forming, or rubbernecking could be the analogy. So what you see here is a little red agent and then the blue. What you'll see is the cars are moving forward, but by these simple rules, the traffic jam is coming backwards. So that's one thing here. We can model individual speeds, so the speed of, say, the red car going up and down as traffic changes. We can also sort of look at sort of the average speed of all traffic as they're moving through the system. So agent-based models allow us to capture individual information and also more aggregate information as we go through there. Okay, and as Sarah mentioned, sometimes we can do things in simulation that we can't do in reality, or we can build a simulation model and then test it in reality if we want to. So we can't set a building on fire or we'll get arrested, but we can simulate a building on fire and see how people might evacuate from those buildings, or what happens if you put an obstacle near a door, how that can potentially increase the flow out of the building during an evacuation type of scenario. Or we can test the models in reality. So this is sort of the same, sorry, the sound is on, so I can hear. Let me just number the sound on that. This is the same type of model. So the idea is, are models any good? Do they match reality? So, and here, some Japanese researchers got 22 cars and a car park, and I forget, do you call them car parks in America? You do, right? And they asked the drivers to drive around at a constant speed, and basically the drivers couldn't keep driving at a constant speed, and they ended up getting rubbernecking and basically causing sort of this shockwave to propagate back through the system, exactly what we see in the simple NetLogo model. The difference is that NetLogo model was created, it's very simple, can be created quickly and then extended to thousands of cars if you want to, or different road configurations. Here we have a specific instance of just one example of a simulation, of one example of a simulation, like in this simulation being the real world situation, really. But the idea is we can build models to either test, explore things in the real world, or to do various other things. Now, one of the classic models in social simulation and agent-based modeling is, and also is the Schelling segregation model. The basic premise of this model is that why do neighborhoods segregate? Why do some neighborhoods segregate? And from a geographical point of view, we'll only see segregated neighborhoods once they've occurred or have emerged, right? And therefore, it's very hard to do anything once that happens. But through simulation, we can explore what might happen, or what might be the reasons for these segregation to occur by giving mild tastes and preferences to many different agents. Here we have red and blue agents. Each have a preference for different neighborhood. In these types of models, the neighborhood is defined by your 8 surrounding cells. So this agent here will look at its surrounding cells and say, well, if I want my neighborhood to be 30% like me, is that the case? If not, I'll move to a new location. And the idea is a very simple model leads to segregation. Sarah?
Yeah, I just wanted to note that in this and the subsequent ones and the example we will use, so there's red and blue types. The black cells refer to vacant ones. So those are going to be among the set that each of the agents in question can choose from.
Okay. So we can create a model, and we'll be doing this ourselves in a little while. So the idea is we create a individual agency, so red and blue. Black is unoccupied, and we can give them preferences. So in this scenario, each agent wants to live in a neighborhood where 25% of the neighbors are like themselves. So it looks at the surrounding areas and then calculates, am I happy? If I'm not happy, I move to a new location. And nothing. And what you see from that simple thought experiment is that basically you don't really see strong patterns of segregation. But if we increase the preference to say 50% and we can run the model, we can see how starker patterns of segregation are emerging as people have stronger preferences to be located amongst groups here. And we're recording the percentage who are similar and of agents who don't like their neighborhood. So the simulation stops when everyone is satisfied with their neighborhood. What's interesting is in this scenario, we only say 50% of the neighbors should be should have similar. They only want to live in a neighborhood where 50% of the neighbors are like themselves. But that 50% preference leads to basically a similarity index of around 80% or nearly 90%. So, you know, mild preferences, I don't know if 50% is mild preference or not, but that mild people only live in a neighborhood who have people like yourself will lead to more extreme segregation. And then we can go, what happens if people really wanted to segregate a lot? How does that change? And here we can run with more segregation and see how more distinct patterns of segregation occur.
So I just want to add, because we're going to do this one in the example, a version of this. Another interesting point is around like 30%, where you wouldn't normally expect that to generate a lot of segregation, but yet that can still generate these patterns. And this is, of course, it's a relationship not only of the function of the homophily preference, we'll say, you know, those percentage of your neighbors that you prefer to be like yourself as defined by this, but it's also related to how much vacancy there is. So that, you know, there would be other little parameters that you can explore with this. Now, I know, Andrew, we talked separately about how this is different from a cellular automata, right? So some of the cellular automata models look a lot like what we'll see in some of the agent-based models. What do you say is the difference there?
So the big difference between this and cellular automata models is that in agent-based models, the agent's actually moving. In this example, the agent's actually moving. In a cellular automata models, the cells just change state. So there's no real movement in CA models. In CA models, all cells have the same rule set. And so they have the transition rule from saying dead or going from dead or alive or whatnot. And just to
but you could have an agent-based model though that doesn't involve movement, right?
That's very true. We can have agent-based models that don't involve movement, but in a CA like the game of life, which let me open file model library. So NetLogo has many examples. The classic one being sort of Conway's game of life, and we have cells, and what we'll just go. We'll see here. It looks like there's movement of cells, but there's no real movement. The cell in this model, the cells, the automata, I should say, are just querying their environment, their surrounding neighbors, and then based on certain rule set, they'll switch state from dead or alive, or in this color, magenta to turquoise. But there's no movement, but all cells are treated the same. They all have the same behavioral rule set, which is not necessarily, I don't think, the case for agent-based models where we have heterogeneity in rules and decision making.
Yeah, I guess I would say that, you know, it's having a conceptually distinct entity that is the occupant of the cell versus the cell itself, and whether you're thinking of that cell as basically inert, as in the game of life, you know, the cell is just having a binary state change based on the rule of its neighbors, but that there's something separate from this, which is in this case the occupant of the cell that's moving in this case. But we can have agent-based models where movement is not happening, and yet we still have something distinct, which reflects the fact that it has some simulated agency, at least. Okay, you can go ahead, Andrew. I know we're
no worries. And you guys might be wondering, like, you know, from these simple abstract models, you know, what can you do with these types of things? Well, Schelling sort of idea, and we should know that Schelling got a Nobel Prize in economics, not for various works with respect to complexity and so forth. There's also, but other people have adapted this using real world data. So there's a study from Tel Aviv by Isaac Benison, one of the sort of pioneers of geographical agent-based models, who, instead of just saying mild different preferences for one group, there are other ways of creating segregation. So he got access to data from the Israeli census going back from 1955 to 1995. And through simple data analysis, he realized that people could have preferences for building types, but also for neighbors. Who do you want your neighbors to be? And so he could basically take the abstract notions that came out of the Schelling model and apply it to a real world case study, really, is what he was trying to say here. And when people are upset or they have some type of dissidence here, is a, I guess, a politically correct way of saying it, agents move. And so just to get, but in his model, because he's using geographical space, unlike in the Schelling model that we explored a couple of slides back, agents were looking at the 8 surrounding cells. Here, one has to define a neighborhood. In the neighborhood here, he's using a Voronoi tessellation of space, and basically any house or building that's connected to the current land, next to the land parcel I'm at, is classed as a neighborhood. Neighborhoods mean many different things to many different people, and there's always a debate in geography, really, what is a neighborhood, I would say. But this is how they define the calculate distance. What is the current neighborhood situation? They had lots of information on the building stock of Jaffa, this small area of Tel Aviv, so they knew where the tower blocks were, what were the more low-rise types of buildings available. They had segregation indices from the census, and then they could build a model from 1955 and try to simulate what might be the residential patterns of segregation. And it gets relatively, flipping between the real world and simulation results, they're relatively similar. They're not perfect, but he shows that we can use data to help inform the decision making, or at least help inform what goes on inside the model. So this goes back to the notion that Sarah and I were talking about at the beginning, which is there's various roles and how we can build models. Some might be data driven, some might not be data driven. It depends on what your purpose is. Both show segregation occurs, but one is more abstract and one's more applied. But the purpose of these two models are very different in that situation. I don't know if you want to say something, Sarah. Yeah.
No, I think we're ready.
Okay. So that's sort of like a quick overview of agent-based modeling. Now we want to move onto the tutorial of this. So I would like you guys to build a model. And the resources what we're going to run through for the next 45 minutes is basically all available at this URL, and I think someone's just put it into the chat, hopefully. So you can
yeah, Bruce just put that in the
chat.
Thank you, Bruce.
So you can download the PowerPoint, the PDF of what I'm going to be showing you now, and also the models as we go through this. So if you get lost or make a typo, which is often the case with programming, you can easily keep following along as we move through. And if you have questions, keep moving through. I don't know how many people have downloaded NetLogo before this tutorial or not. If you haven't downloaded NetLogo, please download it now. So I don't know if I should give people a minute to download it, or if people can.
Yeah, so if you have it downloaded, go ahead and open it up. And let me see, I can try to retype this in the chat real quick, so it's convenient if you want to get it.
I can copy it.
Are you going to do that? Okay. All right. You do that then.
Yeah.
In case you need it, Andrew will put the link back in the chat for you. And so, so Andrew's going to walk through this tutorial. And like he said, in that folder, you'll find the PDF of the specific tutorial slides and the steps, and then each of the NetLogo files for reference. So if you want to see if you are following it as intended, you can check that, but do feel free to type stuff in the chat. I'll keep monitoring it while he's presenting what to do here. Okay.
Yes. So once you have downloaded the file, hopefully you'll see something like this, where we have NetLogo step 0 to step 14. This is my versioning control. NetLogo doesn't do versioning control. So every time I make a major alteration to the model, it's the new, I'll just rename it and create something new. This is just my common practice of me, like in biology, you keep a lab book about, you know, this experiment or this culture was put in there and things like that. In NetLogo, because it doesn't allow versioning, anytime I make changes, I create a new version of it that allows me to help verify, i.e., that anything I haven't introduced bugs into the system.
So but can you clarify,
also,
Andrew, do these correspond though to the steps that we're using in the model?
Yes,
Okay.
exactly. Yes. So as we go through the PowerPoint, which is here, you'll see. There'll be a step. There'll be a step somewhere in there, which. Well, I'll come back to this. Yeah, here in a little bit. Within inside of this. So while people are downloading NetLogo, just let me explain some very simple things about NetLogo before we jump into the tutorial. So NetLogo is based on the Logo language. It's been around for a long time. Often, most NetLogo models have, nearly all the agent-based models have a very similar structure. We have to create our artificial world. We have to populate the artificial world with our agents. Therefore, we have a landscape, so to speak, in there. We ask the agents to do something, and therefore we increment time at that point. We update monitors, plots, anything that we want to do, and then we keep running the model until a certain condition is met. So, for example, we might want to run the model until everyone's happy in their current location, or you might want to, if it's a model of urban growth, you might want to run it until, say, 50 years has passed, and then we stop, write out the files, and then do more analysis on those types of things. But the idea of this type of model is something we start, we finish, and do many things in between, really. Within NetLogo has its own sort of specifics when it comes to what happens, because it's based on logo. We call it, the agents actually called turtles. Turtles are sort of the basic agent in here. Each can have their own agent-specific attributes. So what that means is we can have, you might have agents with different ages, and age increases over time, and sometimes some people might die off or whatnot. NetLogo allows also to have agent types, so red or blue. If you want to build more fancy models, we can have breeds of agents. A breed would be, imagine a wolf-sheep predation model. We have wolves and sheep. Wolves are one breed, sheep are another breed, and they have different rules, potentially. Sheep eat grass, right? While wolves eat sheep. So breeds is a way to basically create different agent types and give them specific rule sets within inside of this. Agents or turtles also are capable of moving, as we talked about earlier. So in the example we'll go through, if an agent's not happy in the current location, it'll move to a new location. Agents sit on top.
Wait, Andrew, could I just chime in on another thing, just in general about agents? Because when you mentioned an agent can get older and die, agents can be dynamically created and destroyed more generally. This is a very useful characteristic. That was all. Go ahead.
No worries. And then, so the agents, one type of entity within NetLogo. Then we have patches, the cell space, the artificial world that the agents sort of inhabit, right? So the patches is our landscape within NetLogo. Like agents themselves, patches can have attributes. So if we were doing, say, so in our example, it would be occupied or not occupied, i.e. is a patch occupied by another agent or not. If you are doing some type of geomorphology type of model, maybe sort of soil erosion, or you might have a digital elevation model. So each cell could represent a certain height of information there. So, but unlike agents, patches don't move. They're always staying where they always stay the same thing. And agents can ask patches for information. So, for example, I can ask a patch if it is that patch currently occupied, yes or no. So turtles can interact with patches, and patches can also count, say, for example, how many people are currently in that one location, and so forth. So
so Andrew, can I say wait, so it is an agent. So ontologically, this is an agent in the
it can be, yes.
Okay.
Yeah.
All right.
Yes, because as Sarah mentioned, agents don't have to move. So, for example, if you're doing economics, it makes very little sense for your agents to move, right? Because if they're just buying and selling stuff, it doesn't matter who they're buying and selling with. It can all be done online. So distance and location makes no difference in those types of scenarios. And then the third type of agent, which we won't talk about today, although I will provide examples of this, are links, which is basically links can be just sort of links between agents, but they are actually their own agent type. So links can be used for, say, representing social networks. Bob is connected to Sarah. Sarah's connected to Andrew and whatnot. And links can move, but only via being attached to other agents. And they don't exist unless there's agents around, or turtles around. But links are used a lot. I use links a lot either for representing social networks, so who's connected to whom within inside of a model. I'll also use links if I'm doing a traffic model. If I want to get agents from one side of campus, one side of UB campus to another side of UB campus, I'll use the links to represent the sidewalk network. And then the agents can use can hop on the links to get across campus using say an A-star algorithm. But links are complicated, and there's no way I can explain them. I'll run through an example of that in 1 or 2 hours, really. But these are the main types. We have turtles, patches, and links. And they all have their own types of attributes inside of this. The data types in here, we have NetLogo supports a whole different range: numeric, floats, like numeric values, integers, floats, and so forth. We can have strings. We can have agent sets or lists, which are similar to like an array list in Java. But the problem of lists in Java, in NetLogo, is that they are unsorted. So they're more like a bag of agents, and which one gets out is always random. So if you want to, so there is issues of accessing objects from a list, which you wouldn't have if you were using, say, Java or Java programming like Mason or Repast. And we can also, NetLogo has been around for a long time, and so we can use matrices from a math package. There's a lot of other types of things. There's ways of GIS packages that gives us vector and raster data structures and things like that. But you can anything you can represent in Java, you can roughly do in NetLogo. In NetLogo, we have variables. Variables are weakly typed, unlike in Java, where they are a more stronger type. So in Java, we would have to declare the variable type. In NetLogo, we don't have to do that, and you'll see an example of that as we go through. Yeah, variables can be assigned at different types at runtime and also during the model. And variables are not case specific. So if you do uppercase, camel case, combination of case, it doesn't matter. NetLogo will be able to handle that. So we have variables that can be changed during the runtime of the model and during the simulation itself. We also have global variables. global variables can be read and write anywhere from NetLogo program. So some of the variables are guaranteed within specific procedures or classes if you were more Java orientated. Other things will be can be accessed anywhere in the program. So, and I'll hopefully make that clear as we go through this tutorial. So we have local variables. Local variables are declared using let and set, and we'll see examples of this as we go through the tutorial. I already mentioned that agent sets are sort of a bag of agents, and then we have booleans, which will say, are you happy or sad, true or false types of things that will capture also in these types of models. So NetLogo is a full functioning sort of language, so to speak, and we can do many different things within it. I'll skip that one for the time being. Basically, when we code, just be consistent with coding. I'm only touching the surface of NetLogo. NetLogo comes with loads of documentation, and it's really useful for that. It has a really active user group. If you put stuff on, say, out there on discussion boards and things like that, people answer your questions super fast. There's also a lot of resources with respect to NetLogo on the NetLogo website itself.
Yeah, I would just add, so you can find a lot of examples there, and then for each example description, they'll suggest how you should cite it, both the model itself and any documentation related to it.
Yeah, and because it's got its own language and its own sort of flavor of things, they also have a large dictionary of model type of commands and things like that. So the NetLogo has a dictionary, which is super useful. And through this tutorial, I'll show you, if you don't know what a certain command is, if we right click on that command, it'll take you to that NetLogo dictionary and tell you what it expects as an input and what it will do as an output, and vice versa. So NetLogo has loads of documentation out there, just if you want to do more types of things after this tutorial. NetLogo has 3 components. We have the graphical user interface, is what you're seeing here. We have a tab that allows you to show information about the model, and then the code tab. We can create, using this button icon here, we can create sliders. So how many agents do we want? What preferences do we want to give the agents? Those are examples of sliders. We can have buttons that execute the model, or set up the model, or execute it, go, and we'll go for examples of that. We can also type things into the command prompt. So you can type in, if you're in the observer setting, the observer is somebody who's watching the model. So it's the god, so to speak. You can say setup there, and it'll automatically create setup. But a very simple user interface is really what I'm trying to say here. The way NetLogo works is we have the observer. The observer is sort of just watching what's happening. The all-seeing Meduse, all-seeing God. We have our patches, and we have our agents, or turtles. In this example, we have wolves and sheep. And if we opened up a simple NetLogo model, like the wolf-sheep predation model, so NetLogo comes with lots and lots of model libraries, which I think is really quite useful. So if you just go to open NetLogo file model library, I'll just clear that. There's, as I say, lots of different types of models. One bit is like a whole bunch of code snippets that do certain, will give you examples of what things can be done. But here I wanted just to show you the wolf sheep example. Which is sort of a classic model in biology. So we have our wolves, our sheep, the wolves eat the sheep eat the grass. We can have grass grow on, and by just pressing the go button in this example, it's calling the model wolves eating sheep, or sheep eating grass, and we'll get various population curves occurring. But what I wanted to show is, we have agents, the turtle, the sheep, for example, have specific attributes. So, for example, we know it's a sheep breed. We know where it's located in the world, and we know some other things. For example, probably how much what else do we how much energy it has. Energy it gets from eating grass, for example, in this example. And the same for the walls, same for the patches. Everything can be queried, everything can be reset, and vice versa as you go through a simulation. So the idea is, in NetLogo, we have observers, turtles, and patches. Turtles and patches can read and set observer variables, but the observer cannot set or cannot set and do it the other way around. And we can capture many of those things. One thing you'll see in these models is these are simulation models. We don't know what's going to happen in this simulation until we run it. As we run it, we go through time. In NetLogo, time is called ticks. And in other simulations, it might be like Mason uses steps, and so does repast. But tick is a time increment. What is time depends on the application. Here, in the example that we're doing today, time is going to be very notional. But time, you can have time, for example, in a pedestrian model, I said, these time step, how an agent going from one place to another place might be every second, or how quickly one walks. Or in a residential decision model, time might be a time period might be 1 year. We ask turtles to do something, and then we set. So once a turtle's been asked, we can say ask turtle, and then set a color to those types of things, set a color to it. So observers can always ask what's happening in the simulation. And you can then say, if I ask a turtle, are you sick? You can then say, if you are sick, set the color to be this. So the idea is a simple command can be turtle agents can be queried, and something can be set and visualized. This is really what I'm trying to say here. So, and this is how we can record simulation information and output that in a simulation. So if you all have NetLogo open, if you just go to File, New, you can do this either command line or not. But we can create like a random model, and in the observer prompt we can ask. So that's the command. Patches are the patches, and you can say ask patches and then say set p color. P color just means patch color, and it's spelled the American way of color, which always confuses me. And we'll say ask patches to be blue, and I get an error because there's no space there and a space there, and also I spelled color wrong. And we can type things in the command line and observe those things. Is really what I was trying to say there. And I use that often, the feature in the observer prompt, just to actually quickly test things like, does the setup work? So if I want to see what, say, this color scheme might look like, I might do that. Or if I want to record certain variables, I can do the ask set types of things. But I know that we have over 50, this will take me 40 minutes or more, so I'm going to just jump ahead. But you can ask turtles to do many different things. We can diffuse the landscape and whatnot. But turning to the model itself, we want to talk about the segregation model, just to give you some context before jumping into the model. So the simple research question, or the purpose of this model, is, do segregated neighborhoods emerge from individual preferences? And we threw in this example from Eric Fisher, who did a lot of visualizations of census data in the past, and just eyeballing Each dot here is basically from the census. Each dot is about 25 people. Red is white people, blue is black, green is Asian, orange is Hispanic. And just eyeballing this, you can sort of see it looks like there is some type of segregation occurring here. So the question is why? And it goes back to what we were talking about earlier. And we assume here that the agents, or our assumption when building this model, and it's also what we're going to code, is that individual agents only care about the composition of their local neighborhood. They don't care about what's happening on the other side of Brooklyn or what's happening on the other, they care about what's happening in their immediate surrounding area, their 8 surrounding cells. So you've all created a sort of a new model. And when we build, so we talk about the interface, but all the code in a NetLogo model will go into the code tab. So as you follow along here, it's always good practice to document the model. So every line you'll see as we go through here, now I'm in step 0. So if you actually went to the thing you downloaded and uploaded step 0, you'll have the code, only this thing into the code block. Just move format so it's a bit bigger. So here, it's always good practice to have some type of header information. Why? If you come back to a model 10 years after you've created it, it's useful to know what's being created. In NetLogo, we can also use semicolon for comment, the semicolon for comments. If I make this bigger, hopefully you guys can see this. So we can semicolon is a comment tab, so anything you type inside of there will not be executed by the NetLogo. Just like first, let's just create a very simple header block of some information. You don't have to do this, but I know that when I've come back to NetLogo models after several years, it's useful to know what it does and why it does it. So, and if you look at the code at step 14, you'll see a very detailed commented model. And that's purely there so for your reference. So when you leave today, you know why you've done what you've done within inside of this. I also normally have like my name and also the date, just so I know when I changed things and whatnot. And that goes back to my lab book. Once you've created the model, save your model somewhere. So I'm just going to save this to my desktop, and I'll just call it model. Model V1, and just save it somewhere locally so you remember where it is on that. So now I want to go about answering that question: do mild preferences lead to segregation occurring? To do that, we need to create agents. We need to create the world. In NetLogo speak, set this up. We need to then tell the agents what to do every time step. We need to be able to record some things on here to see what's happening. That's very useful for sort of visual debugging. And then just keep moving through the tutorial, moving through the logic here. So the first thing we want to do is we want to create this artificial world. So we want to basically set up the model. So if we went over to the interface tab of the model and go to button, and then select the button and just type in here, and we're just going to call this setup. And you can have this is the command. So when I said ask patches p color blue, that was a command. Here is the same thing. We'll build up the setup command. You might want to give it a more useful name or something that is, not lowercase. So here I've just created a simple button called setup, but it doesn't do anything. You get a red error. NetLogo is very good at telling you when you've made a mistake. And basically what it's doing here is that it's saying, great, you've calling a command called setup, but in the code tab, there is no command or procedure called setup. So we want to create this setup command, so the rudiments of a NetLogo model. what do we want to do at setup? What do we want to create at initialization? We want to create some agents, randomly throw them into the system, and yeah, reinstate the system, which means just create it, set it up. To do that, we need some scaffolding. So the functioning scaffolding in NetLogo. Nearly all NetLogo models will follow the same type of scaffolding procedure. We have globals. Globals are variables that can be accessed and set anywhere into the model. We want to give turtles some properties. So the agents in our model are called turtles. Remember, that's NetLogo speak for agents. And we want to say turtles have turtles own just means turtles own these properties, and these properties are only available to the only set to the turtles. We might want to give the patches properties also. So, you know, if we're building a more fancy model, the patches might own elevation or land prices or other things. But the first thing we want to do is say NetLogo, the functioning is all NetLogo models need these sort of the global parameters to be set, what the turtles are, what the patches are. But we also want to set the model up. And to do that, we need to create a procedure called setup. In the setup procedure, all NetLogo procedures start with a 2 and end in an end. And anything so, and then the norm is to say given a name setup, and then it knows to go always to go to setup first. Then we want to clear all, get rid of everything, and then we'll end setup. And over the course of the tutorial, we'll add more complexity to this setup procedure. And we'll do the same with the go, because we want to iterate through the model as we go through this.
So I just want to. Oh
yeah.
yeah, I just want to add that. So if you have the PDF handy, you can copy from that. I also put the lines of code directly in the chat so that you can see what we're starting with here with these 3. And then Andrew, I assume if we were defining links, we would also have something that said links own, right? But we're not doing that. Okay, because those were the 3 classic types, right?
Yeah. But I'll get back to links at the end of the tutorial. If we have time, I can show you some work examples of those as we go through. So now we have functioning scaffold. I just couldn't paste it what we were talking about here.
There's also a question. Right? There's a question too, Andrew. Are these the built-in libraries that we're just instantiating?
This is sort of instantiating the agents based on the built-in functionality of NetLogo, if that makes sense. These are like the scaffolding that one needs to be able to create a model. If you wanted other types of libraries in NetLogo, it'd be like you'd have to just type in the library name on top, like GIS library or CSV library or NW, I think is for networks. With inside of here. But yeah, this is literally the scaffolding for a simple NetLogo model. Did that answer the question or not, Sarah? You muted? Or I can't.
I'm sorry, I was just repeating the question, but I think the person who asked can answer or can follow up if there's further confusion. I think.
Okay. Okay, and so here is like Sarah said, you can just cut and paste the code. This is more details of really what's happening inside of this. Now, nice thing about NetLogo, it automatically indents the code for you if you want to. You can also check if there's any errors by pressing the check button, and it'll check, and hopefully there's no errors. Yes, there's not. I'm going to save this because it's always good practice to save things. Now, if I do setup, basically nothing happens, right? Because all it does is clear all. And now we need to add some more details to that. But it also, if I went in the observer prompt, if I type go, I'll also get an issue with ticks because nothing has been reset with ticks yet. And we'll come back to this later as well. But basically, what we're going to do now is sort of that's the basic model. That's the basic setup. Now we need to add a bit more complications to that model as we go through. So this one is, what do you want the turtles to have, the agents in this model? The agents again want to we want the agents to know certain things. Are they currently happy in their current location? If they're not happy, we're going to move. So we'll create a move procedure for that. They need to calculate how many people live near them that are similar, how many people are not like them in their neighborhood. And we also need to give them the number of agents, because if they're going to calculate how many agents of a certain type are within my neighborhood, they need to know those 3 things within inside of that.
And I just want to clarify,
So really,
Andrew, so these are again posted in the chat, but just to be clear, you're reusing the existing brackets that were set up for Turtle's own. So this should actually go within the,
yes,
right?
Exactly.
So the part that you want is the meat of the sandwich.
Yes, exactly. So here, I'm just going to say happy, and that's a Boolean. Anything in NetLogo with a question mark is a Boolean, true or false. And you notice that I haven't defined what's similar nearby, or what type of object type similar nearby, or other nearby, or total nearby is. We'll do that in a little bit. So we can create the turtle's own attributes. I'm just going to put some spaces in here, and we'll check that works. Yep, and no errors. So these are basically attributes to the turtles, attributes that the turtles own themselves. So right, and now, so we've given the turtle some attributes. Next, we want to actually go into the globals. What do we want to record as we're running through this model, right? What do we want to record? So again, these are global attributes that can be accessed anywhere inside of the model. So here we want to record, say, what is the density of the neighborhood? How many percent similar is basically what percentage of the agent, what preference do agents have? So in this model, we're just going to give agents all the same preference. And here's, so it's going to be a global, so they can query, so they can query that. We want to record how many agents are unhappy at any one time. So why are they? Because if you're unhappy, you want to move, but we want to also record that, because we want to record how the system changes over time. Density, as Sarah mentioned earlier, and those black spaces. So how much black space or empty spaces do you want in the model? We'll come back to that. And then and then percent similar wanted. Sorry, percent similar and percent similar wanted. Percent similar is this aggregate of how many agents. What is the overall segregation of the neighborhood? While percent similar wanted is the preference that that agent has. And again,
so what you're saying is because this is what I was calling the homophily preference earlier, and this is globally defined and uniformly applied. Is that correct, Andrew? In this instance, that's
correct. Yeah.
So and exactly. So I want to distinguish. So the turtles and the globals here. The turtles are agents with limited knowledge. So when we're in the turtle category, we know ourselves and our neighbors, and we're making decisions on that. And the agent then can go up and access something like, say, my preference parameter, if that's universally defined, from the global level. And so there can be some relationships between these, but we're capturing what I like to say, the view of God at the global level, or in any logic, this is the main class, they call it. And that this will allow you to have access to parameters that are defined throughout the model.
Yeah, very, very well said. So now we have the rudiments. We have the globals that can be accessed anywhere. The turtles have their own preferences with inside of this. And
just to be clear, as before, that stuff went up within the brackets of the topmost line where we had put globals before.
Yes. So here, and it doesn't matter where you place any of this stuff in NetLogo, the globals, the turtles, the patches, the setup, the go, it can be anywhere. You can be mix and match, but the convention is always to put globals and turtles and like the stuff that doesn't change at the top of the code, and then set up, then go, and then any other stuff that we're going to create later, like get the agents to move from one location to another, is to place that lower down into the code blocks. But there's no strong convention of where one places what not in NetLogo. It's very up to you what you want to do. Also, you've probably noticed that I'm adding lots of things to here, and you have different colors and whatnot. But if you want to know more about what's happening here, I mentioned earlier that NetLogo has a very strong dictionary, a lot of online information. If you right click on any of the NetLogo specific commands, so turtle zone is a NetLogo specific command, while these are what we've declared ourselves. But if you right click on any of these, you can go quick help. That quick help will take you to that entity or that command or function in NetLogo. So it gives you an idea of what it means. So it gives you more information. This is useful if you're trying to really understand why is this not working or what's happening inside of the model. So we've got the basics. Now we just want to create some agents inside of the model. So we're going to remember we're going to instantiate the world. We're going to generate a random number of agents. It's always good practice just to clear all at the beginning of this, like we already have in the code. We want to then sprout. In NetLogo, the command for generating agents on a patch is called sprout. So we're going to ask the patches to create agents. We'll be asking the patches why they're going to create agents, because we want one agent per patch, right? If you just wanted agents randomly created in one location, you wouldn't have to do this. But here we want one agent per patch. So we want to ask the patches to generate some agents, and I'm setting the density. I want 10% of the area to be empty, right? And I'm asking each patch if basically the randomization has not hit the 190%, you're going to create one turtle, and you're going to set the color of the turtle to be red or green. I guess I could have turned that blue, and that would have been like this earlier example. And what this does is it randomly picks red or green agent, chooses a random red or green agent to populate on a patch. And then also one thing that we didn't do earlier was reset the ticks. So I just want to reset the clock counter within inside the model. So the idea is we can ask something to do something. We can set inside of this, and here this density value is a global. So we can set the density value in the patch itself inside this setup procedure, and then that's it really. So I'm just going to copy that over. But this is sort of just creating the scaffolding of what do we want to do, the instantiation of this artificial world with some random agents. We can check that. Go, Sarah, yes.
I just wanted to clarify, when you were defining, these are the sort of the three basic agent types, and then you had said globals. Oh, wait, no, I'm sorry. It was turtles, patches, and links are actually agent types. But we tend to, you're sort of informally kind of referring to like the agents as being the turtle ones because they're active. So,
yes.
So I guess why is it that we would consider patches agents anyhow?
So if the patches weren't, so this is where it gets fuzzy, right? Patches, like in the game of life, each cell is a patch, right? Or each cell could be an automata. That automata can have its own rules. So therefore, it can act as an agent, as you mentioned, as Sarah mentioned. Agents don't have to move, right? So it's just a way of saying I could make all the patches agents if I wanted them to be. But it's just terminology. They can all be agents.
I think, I mean, these are broadly kind of object classes, really. And so they're encapsulated in a similar way. Like the ask function here, we're asking the patches certain information in the setup, and that's occurring, you know, from the global to the patches level within that, and considering each of them distinctly. And so each of these elements has can be encapsulated. I know in any logic or different platforms, there are different ways to distinguish this, and whether you really think of it as an agent when it's something like the main class or the global, where it's not, it may look like an agent, but it's not really acting like an agent. So there's sort of the mechanisms of how the software will fold it in that is standard. And so there's sort of a software definition version of an agent versus maybe a academic. I don't know.
Yeah. No, it's true. Yeah, no, I agree.
Because I know that any logic developers are very unconcerned with calling the main class an agent, even, you know, and you try to wrap your hand around why would that be? And it's just because they're able to replicate it in the same way as sort of a shell in which you can encapsulate other things. All right, well, anyway, we'll keep going. We can return to any questions.
Sorry. So now hopefully you have an interface that looks something like this. And if we press, and if you went back here and press setup, hopefully you have something that looks a bit like this, where we've created a model, where we've created a random number of agents that were sprouting on patches. And if you actually went in and calculated how many cells there were, there should be about 10% of those cells or patches should be empty. Sorry, I keep switching between patches and cells because in GIS terms we call them cells. We would never call them patches, but I'll try to keep calling them patches at the moment. These agents are just randomly distributed, and you'll see there's another nation of these models is that we use a lot of random numbers generators to initialize populations. Every time we press setup, you'll see that basically the number of the setup, the location of where the agents are being generated is always going to be random. In this example, if you want agents specifically at a certain patch, you can do that, and especially if you're using this data to instantiate locations of agents. But here we're randomly creating a population of agents inside the model. But now we have a very boring model, though. The model's not doing anything right interesting now. We have the very basic model. We have agents populated, but we haven't told them what to do. We haven't given them any behaviors inside of this. So now we really want to do that. And we're not going to give our patches any attributes. We're going to skip that for this time thing. But now we want to give the turtles some behaviors to actually do things. And I mentioned earlier that the turtles are going to query their neighborhood. In this type of cell space type model, patch space type of model, neighborhoods can be defined into two major types: the more neighborhood, your 8 surrounding cells, or your 4 surroundings, or north, east, southwest, the von Neumann neighborhood, as the social scientists call it. I think in computer science they just call it 4 cells and 8 cells. But this is how the agents perceive their neighborhood. Remember, these agents in our model are only going to look at the surrounding neighborhood and the 8 surrounding cells. So if this is me, I'd only query my 8 surrounding cells. You might be wondering what happens here or here or here when the agents don't have 8 surrounding cells. In this example, we're using a torus grid. So this part of the world wraps to here, this part of the world wraps to here, and that's use of the torus is just to get rid of boundary effects with respect to neighborhood types. We can turn that off if we want to. So for the application that Sarah and I normally develop, we would never use a torus because this part of the city is not the same part of the city as that part of the city. But in this example, it is totally okay to have a torus type of environment, because we're more interested in preferences leading to patterns of segregation rather than the actual geographical location of where these patterns are occurring.
And Andrew, I just want to call out a question on if you can just go back to the code part where you said we should be able to press setup now, but then you should just see the static distribution on the landscape, right? Because it's not
Yes.
changing yet. And we haven't done anything to
No,
make
no.
it change. So if you're able to get something on the landscape and that should be different each time you press setup, then that
Yes.
is the right point, because the setup is redistributing randomly across the landscape. The other question is about lowercase, uppercase. That should not matter in NetLogo as
It shouldn't, yeah. But the general, well, it will not matter with your variables that you're creating, but it will matter with the commands that you're typing.
Okay, so in this case, there's
I think
not anything but a blank screen. Can you just show your code screen again, Andrew? The code page, and maybe just check that you've got things, because you should now be able to see the red and green turtles on the landscape.
And and yes, and if not, it means you probably miss. If you can't see the agents on the thing, the quick way to check is to press this check mark here to see what error the code is giving you. And if you are getting an error there, it means that there's something mistyped in here. NetLogo is very specific about spacing. So if you put the spacing in the wrong place, or use parentheses rather than square brackets.
Great. It looks like we're all set on that one. Thank you so much, Andrew. I appreciate you going back on that. So yeah, at this point, you should be able to simulate the layout, but you're not getting dynamics, as he was saying, because we haven't encoded the behaviors. So we'll do that next.
Yeah, and just to check that. So here we have setup, and remember we reset the ticks every time. We will see a count of 1. If we type in the observer command go, that's going to call the go procedure that we created. And you can sort of see by me pressing go, the tick count on top of the screen is increasing by 1 every time I type that. And it also remembers what you typed in before, so it sets the background color to be blue if I didn't want black. But I don't like black.
As some of us created a new model. Yeah, there you go.
So,
okay.
So by calling setup, it clears the blanks, it clears away the world and comes back to this, right? So we want to give the turtles some behaviors inside of this model now, right? And in NetLogo we call these procedures. So this is a large chunk of code here, but let me just explain what this is doing. We want to ask the turtles, to calculate the agents who are similar to me nearby. I want to calculate the number of agents who are dissimilar to me nearby. I then want to calculate the total number of agents who are surrounding me. So total nearby similar, right? So that this is I want to calculate total, and to calculate total nearby, I need to add similar nearby, which I've just calculated here, with the other nearby, which I've calculated here. And once I have that, I can then work out if I'm happy, and this is one of those global variables, right? These are the global. Remember, going back to the code base here, we have similar nearby, other nearby, total nearby. So we are calculating what these are based on in this update turtles procedure. And then I can work out if I'm happy if the similar wanted, which is the global, times the total number of agents nearby, is less than a certain percentage. It's really what this is showing you, right? So that's what that procedure is doing. So that's just asking nearby agents. So neighbors by default will capture the eight surrounding cells. So it will create the 8 surrounding cells of where I am. If I said neighbors 4, it would just get the one new neighborhood. But here I want to use the more neighborhood. so really that's what this piece of code is doing. So I'm just going to paste that in here, but by just pasting it in and checking, it's not going to do anything. And the reason it's not going to do anything is that procedure that I've just added is not being called from anywhere, right? So it's actually, and before I press setup and re-instantiate the model, if I click on an agent and say inspect turtle and click on this, I have some attribute information. This is turtle's own data. We can see that currently we don't know if the agents are happy or sad because we haven't set it. We don't know how many agents are nearby of that, and we don't know how many total agents are nearby because we haven't actually called that command. So this command update turtles will actually set these turtle own properties now. But it won't do that unless we call it somewhere. So we're going to add into the setup procedure command update turtles, and we want to do this before resetting the ticks, because there's no point calling this command before we've created the agents as setup, right? Because otherwise you create them and you get an error because, well, you haven't created them. So the way the setup these procedures work, it's sequential. So this gets called first, then this gets called, and then we want to put in the update turtle command just before resetting the clock or the ticks of the model. Oops, and if it's not called the same, it will not find it. Press save. Now, if I went back to the interface tab and press setup, and if I click on an agent and inspect that turtle, I can now have information based on what we just calculated with respect to turtle's own, similar nearby, total number of agents nearby, and are you currently happy, true or false, the Boolean. And you notice I didn't, and this therefore allows us to start migrating through the segregation process. So now we have our agents. These agents know if they are currently happy or sad in their current neighborhood. But that's not really much, right? We might also want to update some of the global variables that we've created so far. So very similar to the way we created, updated the turtle's own properties. We want to also update the global properties of the simulation. So again, we want to work out, for example, percent similar and percent unhappy. So we record those things. But the difference here is that we're going to go through all the agents and calculate these values as we go through. So we're counting turtles here. We're counting all the turtles of the whole simulation. Is what this code block is doing. So again, this is another procedure that we want to have into the NetLogo model. And you might be wondering, you're getting quite a few procedures now. NetLogo tells us if you get a large model, so I have some models that will have like maybe 100 procedures, and to quickly define one that I'm looking for, we can use this drop down to find out where we're going. Similar to the update turtles procedure, if we don't call this, it'll never get updated. So if we want to update, so we're going to add the update procedure command to that same code block and press save. Now we're also going to therefore updating some of the global variables within NetLogo. We can check to make sure there's no errors, save the model so we know what it's doing. And if you
Andrew, can you just scroll up
yeah.
on your code screen so that they can see that where you make sure to put update turtles and update globals is going to be right before resetting the ticks under the setup realm.
Yeah, and again, you don't want to call, as I said, you don't want to call update globals or update turtles before you've actually created the turtles in that sense. So there is a whole area in ABM about activation order. The way you ask the agents to do things will impact the result of your model, but that's much more advanced than what I want to go into today. So you should have something where you've added now added two new procedures and called those procedures from the setup command, like Sarah just asked me to highlight here. So everything is sort of working, should be now, but the model's not going to do much. As I say, we can do, if we went back here and press setup, we get a new thing, but you know, I can get the model to run if I want to by just typing in go in the observer prompt, but nothing's happening, right? And it's also quite annoying to always have to type go all the time. We can add another button therefore to advance the simulation. We'll call this go. And again, we're going to call it go, and that's going to call the go procedure, right? This is a simple way of doing that. And we'll just say, okay, you can you can click on any button if you want and move them around. So you can make a graphical user interface a bit more fancy or more visual if you want to. But if you press now, instead of having to type go, I can just press this button, go, 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 and you can sort of see the tick counter advancing, but nothing's happening. You know, the agents are not moving, even if they're upset. And that's one thing that we need to address. We need to get the agents to move here, but we are advancing, addressing the global variables, updating, and the unhappy variables. So we want to do add some code to make the system a bit more interactive, to evolve, so to speak. So here we want to add code to the go procedure. What this code is going to do, just to give you a say, I want to say if all turtles are happy. Remember, happy is Boolean. I'm going to stop the model. There's no point running the clock cycles out. If the agents are not all happy, then this procedure is going to be called, which is move unhappy turtles. Of course, we don't have that. We haven't created that procedure yet, so we'll create that procedure. We'll update the turtles and we'll update the globals. So every tick, and we've already got these two procedures created, right? So we're going to add this bit of code to the go procedure. At the moment, the go only has tick. We're just going to place this before incrementing the tick for the counter. Why do you do that? You want to probably it's always this. You always should update the time step once all the agents have had the option to do something. So this is why all those things are going before. Update turtles, update globals is the same as what we had before. But if we press save, we'll get an error. That's because we've not created anything here that asks that tells the agents how to move. So we need to turn to that. And again, the stop command is a specific feature in NetLogo, and it basically tells the simulation to stop if a certain command is met. So again, if you don't know what the commands mean, please right click and find out. You can find out more. And I think that's quite useful. So errors happen, and you should all get an error there. So that's not a problem. I'm looking at the time and realizing that this is going much slower than Sarah and I had practiced. And we had actually, so let me just try to go through some of the logic a bit more quicker here. So we want to move the turtles, and I don't like having really long procedures because you might want to change things as you go through. So, right. So I'm going to create one procedure, which is ask agents who are not happy, find a new spot. But this also demonstrates how I can call a procedure from another procedure, this one, from an existing procedure. So the idea is that we can call procedures from all over the place. So this is my move unhappy turtles procedure. And if you're following along, we're in step 9 now, which is the file number.
And I'm also copying these in the chat too.
Okay, awesome. Thank you so much. As we move, so here we ask the turtles to move if they're not happy, then they have to find a new spot. Of course, we haven't, how they do this. This is quite simple. Well, it is relatively simple. In the Schelling model, you should find a nearest spot where your preferences are met. But in this example, we're just finding a random new spot. So we're going to say find a new spot. You're going to choose a random RT to choose a random direction somewhere. So I should have said turtles have a heading. All turtles are looking a certain direction. At the moment, that's very random. Here, the turtles are going to randomly choose anything in around 360 degrees of themselves. They're then going to move forward a random number between 0 and 10, or 0 and 10. So and that's what FD means. It means forward random number between 0 and 10, because that's the 10 command, right? It could be 20 and it would move forward 20 steps, up to 20 steps. But before moving to that location, it's going to ask if there's an existing turtle there, because you can only have one agent per cell in this example. If there is a turtle there, you just come back to this program again. If not, you move to that patch. That's all this is doing. So this is just a very simple loop in NetLogo speak. So now, if we paste that there, press save, our arrow's gone because we've created that move unhappy turtles command, and we are getting the agents to move. So now if we went back to the setup command, it still works. The go command, nothing's now it's not working. This is because every agent, anyone want to guess why? If I was in PowerPoint mode, you would have seen this. The reason the model is not advancing one step at a time is because we actually had in the code, this code block. Where is it? I'm going to go to go. If all turtles are happy, stop the model. The thing is, we haven't given the agents yet a preference. What is their happiness value? So at the moment, all agents are happy because we haven't actually given them this notion of similar wanted, which is a global. At the moment, that's 0. So of course the agents are happy because they have nothing there. So we want to add into the code block at setup %similar wanted. I'm going to just hard code this in for the time being. So it's setup. We want to add, before creating the agent, set the global, because we want to give the agents a preference as they're being created. Set up, no, sorry, it doesn't matter. You could have it here, or we could have the set preference here. But I think it just makes sense to have it before creating the agents themselves, just from a logical point of view. I want to set the global here and then create the agents, then give them the agent's value. Or it could be called there, it wouldn't make any difference. Now, if we press save and press setup and press go, we can now advance the simulation and we can sort of see segregation occurring. If we went back to the code and changed that preference value to say something higher, say 90%, 90, now they want us to live in a neighborhood where 90% is, press setup. We can press go a lot of time and it might settle or might not settle. But basically, we can create the setup, but if you didn't set the global variable, the model logic's broken. And this is the other thing about agent-based modeling. What you put into the model is how the model behaves. The novelty is not knowing how all these things are going to interact, but you are creating the model.
So what you can do at this point is you can adjust that number as Andrew just showed. So from the 50, which is the example, the 50% threshold is the example in the tutorial, you could make it 90, you can make it 30. And again, these are percentages being applied to just, a group of 8 neighbors. So consider how that plays out. And then, so Andrew, just in the interest of time, I don't know, do you want to go through adding the buttons, or should we just let, I think people can explore those additional ways to add the levers to be able to quickly change that, and also to show the plots over time, so that we're considering not just the spatial pattern at a point in time. But yeah, I don't think we're going to have a lot of time to go through a bunch of extra examples. I just want to make sure if there's any general questions or concerns that we'll have time for that. So, but if you, only if you agree, Andrew.
No, that's totally fine. Let me just jump to like you can do a lot with NetLogo. So the tutorial and the PDF that you can follow through in your own time allows you to do many things. You might want to also make, like, you can change the graphical user interface, make the smiley faces, sad faces within the model to make them happy. And we sort of already, you've already, if you upload step 14 of the model, open.
Right. Yeah, so you can build out or pull up the fully developed example. There's also example Schelling models in the NetLogo library, as with other libraries too.
And you can, you know, I like having smiley faces or upset faces because that tells me if the happy Boolean, true or false, is working or not for me. And you know, we can set up and go, and you can play around with different percentages wanted and see how different patterns emerge. If you set up to 100% preference and go, everyone's going to be upset for a long time because it's very hard to meet. But this is a very simple NetLogo model, and NetLogo is super powerful. You can do lots of things with it. Just to give you an idea, instead of just using patches, we can use polygons. So census tracts, for example, we can instantiate those agents based on. So in this example, it's exactly the same as the one that you just had. The only difference here is that the neighborhood is based on the surrounding polygons. So this agent's neighbors are all the polygons that are touching this polygon. And this is called DC segregation underscore DC underscore 1 in NetLogo, and that's directly reading in a shapefile if you're a GIS thing. We can also instantiate a world based on agents. So in the example that we just sort of going through earlier, the agents in that simple example are randomly sprouted on the patches. But if you have data to tell the agents where exactly they want to be located, like in this example, you're reading in from a database file saying create 10 agents or create X number of red agents in this one area, you can do that. You can also do lots of spatial statistics, program many things in NetLogo. What I'm trying to say is NetLogo is super powerful and you can extend any way you want to do it. And it's the graphical user interfaces and things that are super intuitive. There's lots of examples out there, and I don't know where we should go to now, Sarah.
Can you just jump to the, if you could just jump to the pattern oriented modeling slide, the one with the feedback loop, and then we'll skip through just a couple of those. I think that would be good.
Okay.
So as we talk about the time permitting, also there is a good question, but let me just introduce this slide. I would go through a more detailed example. I won't go into detail, but I do want to point out, so that as we said at the beginning, there's sort of two aspects of data. We're generating data with any model we built, however wrong it may be. And we want to make use of that for model analysis. That's why we see patterns coming out of model analysis. And then, but there's also, we want to make use of patterns in informing the model structure. So this is consistent with a broader view of modeling as an iterative process. Andrew, let's see, from here, could you just go to the slide on the calibration specifically with that overview? Do you know which one I'm talking about? The pattern oriented. It's again the Grimm and Railsback further down, actually. And so in the meantime, I'm going to read the question, but you know which one I'm talking about, the one that has like how you would do it. Not further down from that. No, further.
This one.
No, later. We don't have enough time for all that. So I just want you to go.
This one.
No.
No.
It's before the maps, Andrew. It's 2 slides before the maps. That one. Thank you. All right.
Sorry.
So I'm gonna just have that up while I also. So this is an illustration from the same source, Grimm and Railsback. Their book. Individual-based modeling and ecology, which applies to agent-based modeling, had a good overview of how one might make use of data. So in the modeling process where data is, if you know the parameter, you just set it with what you know. If you don't know, you want to identify a range over which to test. And then in terms of specifying model structure alternatives, this is where you might break or turn on or turn off certain structural features of the model that and test those out. And we want to identify some observed patterns in the real world as filters when we think of calibration. For each alternative, we'll systematically vary the parameters, compare the simulation to the observed, and try to somehow minimize that. And then for best fit models, we sort of filter from that to select some for further analysis. And I had an example, but Andrew, I don't want to go through it. What I'd like to do is make sure to address the question that came up. Can you see this question too? It says, there are several parameters in making a model, thinking of traditional Bayesian approaches toward taking a traditional Bayesian approach toward quantifying results or optimization, but there is no obvious way to construct a likelihood function with agent-based models. Can you comment on quantifying results and extracting statistical information from the model? And so this is, again, in thinking of model analysis. So what do you do afterward? Did you want to say something about that, Andrew?
I don't really know the answer. There's no.
Well, I mean, you can export. I mean, I guess I would say at first glance, any modeling platform, you can export your data and analyze it however you would. I know that in terms of specifying distribution functions, those can be well specified in the different platforms, depending on what type of a probability distribution that you may want to apply. And Andrew, can you go ahead and go to the one slide that you were about to go to that has the iterative modeling practice? That would be, I think, another useful one to keep up here. So I don't know if you want to say more about that. The results are going to be quantified if you simulate them. So that's, it's a matter of harvesting it.
Yeah, but I guess the question is traditional Bayesian approach, quantifying results, optimization of, I guess the challenge is with here is we're not really necessarily, I guess you could carry out a design of experiments after running the simulations to work out what are the best parameters for a certain thing. But the big question on these types of models for me is, what is the solution? What is the best solution? Or is there a best solution? Or is there a range of solutions? I'm not answering your question there, Bruce.
Can you go up? Wait, can you go up like 5 slides? The one right after the maps. That one, yeah. So this shows an example like where we have an objective function and we're minimizing it over time. And so I want to consider some sort of migration error for my model, and I'll keep track of this over time. And then if you just tab through the next couple slides, Andrew. So this shows me there are some limits as to how good I could get, because I was trying to combine both the directional and the total move error, and I just had some limited data on migration patterns in this case. But if you go to the next one, Andrew, this sort of pertains to the question that came up. I was still able to analyze the broader set of patterns and consider combinations of parameters that could be clustered in different ways. So these are some of the clusters that came out that are basically aggregated, averaged across the different settings from different groups of simulation runs. So in this model, which I didn't go through in detail, the challenge was to try to identify the parameter settings that I didn't know for certain weights of functions about social network choice and neighborhood choice. And so I don't know this information, but I have some information I do know about where people wound up living, but there was a lot of limitations in terms of how much you could really glean from that. So you can go ahead to the end slide. Probably, Andrew, is a good thing at this point since we're running close on time. There's another good question. Did you see it?
Yes, and I guess the question, what is, I don't know enough really what does one, Robert, if you can explain that, unmute and explain a question to me a bit more in maybe we'll give you a more definitive answer.
So I guess I was thinking about what if you're thinking about likelihoods, you're thinking often about like distances from some optimal value of an output, right? And so if you're tracking the number unhappy, or in the car example, you're tracking the pattern of maybe the average velocity. And so do you use that to drive the objective function? Then you vary the parameters for whatever sort of spatial pattern occurs, but you're sort of limited by looking at the quote unquote integral of your temporal spatial pattern. So a limited integral in one sort of in a lower dimensional space.
So I guess, yes, I think is the answer to your question, which is if you're trying to say maximize traffic flow, these are the parameters you can tweak, and this is one that gives you the biggest bang for your buck. That's what one would be trying to explore in this setting, if I'm understanding you correctly.
Okay, yeah, that's what I was trying to get at. So that's how you would you have an output that you have that's sort of an integration of all this material. Then you can actually
Yeah, but to go back onto a comment that Sara made earlier, these models don't give you necessarily one output. That's the problem. So imagine here you get, like in that segregation model, right? At the moment you would have number of unhappy agents. Eventually that's going to be 0, right? If you run the model. But there's other outputs, like your agents have so many different potentially umpteen parameters, all of them slightly different. So I guess it depends on if you want to look at one model output or a whole bunch of different attributes within the thing. I guess,
yeah, we find agent-based. Yeah. Oh, go ahead.
I was going to say optimizing for one output is tricky because, I was going to use an analogy of elections, but I'm not going to do that.
But you have a time series. You could if a time series is varying, I mean, could you track this time series explicitly, or would you impose another functional form that allows you to have an oscillating time series, like a predator-prey model structure, for example? You've got the agent-based articulation, but there's actually a different set of ODEs that can describe that kind of pattern.
Right, you could compare the one to another. That's yeah, that would be quite useful. I know, and so in the system dynamics tradition, you very much would want to get this trend over time was part of the pattern to which you want to align your model, just in terms of a baseline expectation, and then let alone understanding alternative scenarios to that.
Sure. Is it trivial to back extract, let's say, agent level rules? If you do that kind of conversion, let's say you want an insight about individual decision rules from something that's fitting that varying output, for example, to a simplified structure.
Well, oh, you go ahead. I have an answer. Maybe not.
I have an answer as well. I'm curious if my answer is the same as your answer, actually. which is it's not trivial at all, really, because we're talking, I don't know, my answer is like, you have, say, in that example, how many agents? You have basically several set up. We have 690 agents. Each one of them is doing something at in every single time step, trying to understand what behavior led to the whole, like who moved first, potentially have a whole ramification on what happens. It's possible, but
yeah,
it's
like being able to track it. I know there are some people who are, specifically trying to track the trajectories of individual agents. So I guess what I was wanting to address, maybe it's not the same question, or I'm not understanding, but in terms of, could you represent the same structure in a simpler model and like be able to compare and contrast? So in general, like with the ODE or, partition or compartment system dynamics type model where a mathematical expression is feasible, any of those should be able to have an agent-based counterpart that you could try out with comparable assumptions. The reverse is not the case. So if you have something that's been styled in one of these more traditional dimensions, you ought to be able to create sort of an agent-based analog to that you could explore then heterogeneity, network structure, probabilistic, stochastic rules, and things like that. The other big thing that we didn't maybe emphasize enough, but just a little bit, is that with any of these stochastic aspects, the element of chance creates a more realistic world, but it also then brings the imperative needing to do more testing, and then depending on the interface that you're operating in, some lack of ambiguity on what really is happening. Like what is the sequence for agent 0, and at what point in time. Now, I know in the AnyLogic environment I work in, it's, you know, it's pretty easy to drill down to the agents, but in terms of you know, who caught COVID first, and, you know, who spread it to another one, if we're, you know, modeling a contagion model, being able to track that is a little bit more advanced, but people are certainly trying to do it.
Yeah.
Thank you. That was a terrific insight there. So.
And also, I imagine you can do this with NetLogo too, Andrew, you correct me, but I know in AnyLogic you can easily fix the random seed. So if you want to like hold it, you know, here I have a good random landscape, but let me keep it and run some experiments within that.
No, that's very true. You can do that. And just to piggyback on some of what Sarah said, the questions you are asking are very rarely addressed in the agent-based modeling community. So maybe it's a follow-up conversation we can have outside of this, is to talk about these types of things, because outputting the analysis of these models leads to a big data problem. Well, I don't know if it's a big data problem, but at least it can lead to very copious amounts of data that one can then explore in a whole different way.
Which is why I think this is good to discuss, from the data science side, just from the generated data from the enterprise, and systematically keeping track of what resulted from what different assumptions, and being able to replicate that, right, for the scientific enterprise. So there's good, I know probably somewhere in the slide references are the stuff on the ODD structure of approach to modeling. So it's overview, design concepts and details. There's lots of good guidelines by now that we're a couple of generations into this approach to modeling, on sort of standard approaches to it, including those that kind of wrap that within other approaches to simulation modeling. But okay, I'll be quiet. I think we're over time, so I don't want to belabor it.
Sorry about that.
Oh, thank you guys so very much. That was really quite informative.
Thanks for the opportunity. We really appreciate it. And thanks, Andrew, for coming full force on this.
Well, I'm glad you talked me down from the 200 slide deck we had to what we had today.
I know. So you're like, you think this was bad? See what it could have been.
Well, thanks all very much. For everyone in the audience, I just remind you that there's a talk at 3 o'clock on how eBay tells you what else you want to buy, and at 4 o'clock there's a talk by an epidemiologist from Pittsburgh in public health, who's actually using agent-based models to describe the opioid epidemic.
Fantastic. Thank you.
Thanks, guys, so very much. Take care.
Bye. Have a good afternoon.
Thanks.